Okay, so um yeah, today I'm going to record a video. So this um acts as the ninth class of our signals and systems. So we are going to finish this Laplace transform section, and then we will move on to the discrete case. So to get your attendance, please work on the um, short exercise posted in my ITS classroom. So once this video is out, I will tell you through perhaps emails or WhatsApps, and I will make also the corresponding exercise in my ITS classroom. So I believe last time we were somewhere around here where we have the Laplace transform already sorted mostly. So now the next step would be the inverse of the Laplace transform. And if you are talking about the inverse of Laplace transform, we are mainly talking about partial fraction method for this case. So I think we implicitly have done this before, but here is just some of the uh, like a formalization of this method. And yeah, let's see what kind of um, like extension we can get from this. So here we have a rational function in S domain, um, which could be written as this. So n per d would be t1 plus t2 and so on until tk with ti is in form of a over s plus p to the power of n, or bs plus c per s square plus as plus b to the power of m, where the polynomial here is irreducible, so it cannot be factored further. Um, so the idea, is we try to find like what would be the simplest denominator of each terms of this summation of fraction. So the easiest one would be the unique first order factors, where we have first order um, fractions here. So if we have xs is ns per ds, then xs is in the form of ns per s plus p1, s plus p2, and so on until s plus pn. Then we have the a1, a2, a3 until an over s plus p1 until s plus pn. And the idea of this is that we are trying to find this, right? So we know the denominator, but at this point we didn't know yet the numerator. So what is the numerator here? So we have s plus b1 as the denominator, s plus b2, and so on, but we try to find a1, a2, a3 until an. And an is actually could be found by multiplying here s plus pn, and we re-enter or write the fraction n per d, where s is minus pn. And therefore now xs is becoming this summation of several fractions, and then this should be um, doable to process, where we now have the inverse Laplace of this xs. So yeah, and then we have this a1e to the minus p1t plus a2 times e to the minus p2t and so on until an times e to the minus pnt. So that's the non-repeated first order. And if it's repeated, so actually we will just look at the examples later, um, so that we get yeah, more concrete idea. But for the repeated first order, we have repeated terms here. So we have s plus p, we have s plus p square, we have s plus p to the power of the 3, and so on. And here we can use this, let's say, short um, trick, or we can use this short equation, but for the other powers, so an here is for this, but for the other fractions here, so a1, a2, a3, what we need to do is we just use the derivative. So we derive 1 over n minus k factorial, and we multiply this by the derivative of s, and then we multiply this by s plus p to the n times ns uh, per ds, where s is minus p and k here. So k is whichever values satisfy this 1, 2, 3 until n minus 1. So that's for the repeated first order. And then for the second order, the general idea is still the same, and we now have the uh, numerator. So the numerator here is still ns, but we have the form of the like a second order polynomial here. So s square plus p1s plus q1, and this um, is irreducible. So for example, if we have x square plus, let's say, 2x plus 3, the root of this would be imaginary, and we cannot accommodate those imaginary roots. So this, let's say, is one of the irreducible forms. But actually, yeah, for this case, for the second order, it's actually even more restricted. So let's see in the example. And still, the idea is based on this, we try to find the inverse Laplace transform by looking at the table, and we get the pairs. Okay, so let's quickly look at these examples. So example 13, here we have this s minus 2 over s to the 3 plus 5s squared plus 4s. So we factorize this, becomes s times s plus 1 times s plus 4. So then this would be a1 plus A2 plus A3. And to find A1 here, for example, we can get the um, equation. We just plug this into the equation. So, for example, A1 would be S minus 2, and this would be S plus 4, S plus 1, and this would be because A1 is corresponding to S, so this would be just S, where S itself is the value of S that makes the denominator 0, so it would be like this. So this would be minus 2 per um, 4 times 1, so that would be minus 2 per 4, which is minus half. And we get the A2, the value of A2, we get the value of A3 by the same method. Just quick calculation here. A2 would be S minus 2, and this would be S. So A2 is for S plus 1. So this would be S plus 1, S plus 4. So this would be S plus 1, and this would be S equals minus 1. So we cancel this, and we get like minus 3 here. Then we have minus 1 times 3, which is um, yeah, which is 1. So same process for A3. So the end product is we get XS, which is now much simpler. And this will help us to obtain the XT. So by looking at the table, so from this XS, we get XT, which is the inverse Laplace of XS, which is minus half from the um, minus half per S. So this would be the unit step times minus a half. So here would be e to the minus t ut. This would be minus half times e to the minus 40 ut. So that would be the first example. So you don't actually have to do this equation. If you are okay with like doing this uh, with like taking the longer route, you can of course like equates the um, numerator. So for example, okay, so we have s plus 1, s plus 4. So this would be like a1 times s plus 1 times s plus 4 plus, let's say, sorry about this, so a2 times s plus 4, and the last would be a3 plus a3 times s plus 1 times s. This should equals to s minus 2. So if we look only at the numerator, we will get the value of a1. What is a1? Also a2. What is a2? Also a3. What is a3? Um, and then, yeah, we will get the same result for the values of a1, a2, and a3. All right, so we continue to the next example. So here is the example where we have the um, multiple like repeated poles or repeated polynomial equation here. So we have this s square plus 2s plus 1, which could be factored into s plus 1 square. So this is the um, fraction, and then we can get the expansion here into s plus 1 and s plus 1 square. So this would be broke down into this, and here we try to find the um, numerator of this. So the A2 here would be straightforward because we have the s plus 1 square, where s is minus 1. So this would be um, just cancelled, right? And this would be minus 1 plus 2, which is 1, and A1 here, which corresponds to S plus 1, would be D per ds S plus 1 square times S plus 2 per S plus 1 square. So what we do here is actually we actually cancel this, and then we try to find the derivative of this. So the derivative of this is 1, and actually the value of s here doesn't matter because we have 1 times 1 divided by 1 factorial, which is also 1. So this is 1. Thus, we have xs is 1 per s plus 1 plus 1 per s plus 1 square. So xt here, the inverse Laplace of xs would be e to the minus t plus t times e to the minus t ut. So here would be corresponding to this. This is corresponding to this. And I think the first one would be very straightforward. The second one, it's probably a little bit tricky. Perhaps I think it should be better to familiarize with the um, table, or at least for some specific, like for some more specific case like this. All right, so that's for the first order factors. Then we have the second order factors here, second order system. So for the second order system here, we have um, s to the power of 3, or s cubed, plus s square plus 4s plus 4, where yeah, if you are familiar with or you are um, let's say have like some intuition with with this, you can get like s plus 1 times s squared plus 4. But yeah, you may uh, kind of think that, okay, so how do we know that the factorization is like this? So yeah, there is unfortunately no specific or no systematic method to do that, but um, yeah, I think it could be done with a lot of practice. Um, so if we have this s squared plus 4 as the denominator, now the numerator is as plus b. And if we have s plus 1 as the denominator, the numerator would be just c. So the step here would be very similar, unless, well, we have like some like a repeated pose, but we don't have this in this case. So the C part here. So to find C, we could do the usual, where we have the s plus 1 here as the um, factor. So we have s equals minus 1 to in order to make s plus 1 equals 0. So we cancel this out and we have minus 1 plus 6. So this would be 5, of course, and this would be minus 1 square, which is 1 plus 4, which is 5. Then we have 5 per 5, which is 1. Um, and then we get xs is as plus b per s squared plus 4 plus 1 per s plus 1. So this we have to solve this by a conventional way where we um, need to break this down into as squared plus a plus bs plus b plus s squared plus 4. So we group the term, for example, with s squared together, and then we group the term with s together, and we group the constant together, and they have to be s plus 6. And then here we have minus s plus s square plus 2 square, which is 4. So the reason we go into this form is that, well, we want to get s square plus a square. In this case, a is 2. So s square plus 2 square. And then um, we can look at the table to get the corresponding time domain function, which is cos omega 0 t ut. So this would be s per s square plus omega 0 square. And this would be omega 0 per s square plus omega 0 square for the sine. So sorry. Um, xt then, so we get minus s per s square plus 2 square. So this would be omega 0, which is 2. So cos 2t. And this would be the omega 0 here would be 2. So this becomes sine 2t. And this is straightforward. It would be e to the minus t ut. So, yeah, it is a little tricky because we are quite, okay, let me fix this. Sorry. Um, yeah, we have to do a lot of exercise to know where should we go with this kind of form of the fractions. So yeah, in this case, for a second order system, in some cases we will do cosine and sine, and then also together with the first order system. So yeah, that's the um, second order system. So another example here. So example 16, we have um, another irreducible. So for this, it's also irreducible, right? So s squared plus 4, the solution of this would be imaginary, would be like a 2j, for example, or j2. Um, Also similar with this. So for the second order system here in the example 16, we cannot get the root or the um, simple root of this. So instead, we are going to decompose this into like as plus b and c. So c per s, this should be again straightforward. We get the value that makes the fraction here becomes infinity. So this would be 0, of course. That makes the denominator here 0. And this would be 5 per 5, which is 1. And then XS, right? So XS here would be um, yeah, S plus B, now plus 1 per S. And by using the same method, we group this together. So this would be AS plus B, for example, and this would be multiplied by S, and then this would be plus 1, right? Multiplied by s square, sorry, minus 4s plus 5. So this would be um, equal to this, because this is still the same fraction, right? So we group them together. For example, if this is s, so we have a s square plus 1 s square. This would be b s. This would be minus 4, so b minus 4s. And the constant is only 5, so just 5. And this should equal 2s square plus 6s plus 5. So this would be, um, yeah, as. So a plus 1 here would be 2. So this would be, then a would be 1, and b minus 4 would be 6. So this should be, yeah, of course, then b needs to be 10, and 5 is 5. So now we have this xs, and yeah, again, the same trick we use here would be to try to change or to write the polynomial into this form with, let's say, s minus something square plus something, or s minus omega 0 square plus a, for example, to get the trigonometric um, form, or the sinusoidal form, or decayed sinusoidal of these functions in frequency domain. So here s minus 2 becomes e to the 2t cos t, and then 12. So if we have constant here, don't worry about that. If it's just a 12, so it could be multiplied later, and this becomes e to the 2t sine t, and this 1 per s would be just ut. So yeah, there we go. We have the second order system here in the form of the sinusoidals, or in terms of some trigonometric functions. All right, then let us continue into system stability in S domain. Okay, so we are going to continue by um, looking at the system stability of the system here in S domain. So for sure, stability is an important issue in system design, and bounded input, bounded output, or BIBO stability could be analyzed in S domain through transfer functions. And the transfer function of the LTI system, as we knew already, is written as HS, which is the ratio of NS and DS. And if we write it down in form of the partial fraction, we have this one that we just solved before. And we can look at the stability by doing the inverse Laplace so that we obtain the impulse response of the system. Um, but there is actually a simpler way to do that. So we can look at what we call the pole. So the pole is the value that makes the denominator of the transfer function 0. So for example, if we have 1 per s plus 2, then the pole is 2, sorry, minus 2. If we have 1 per s plus 1 times s plus 2, then there are two poles. The first one is minus 1 and the second one is minus 2. So this actually determines the stability of the system. So here the simple pole in the left half plane of S domain, if this is the case, then we have the impulse response of the system in this form where sigma, so sigma here is positive. So this means that we get like e to the minus sigma t, which is a positive value. And since we have negative here, so the entire thing here becomes negative. So this would be, for example, e to the minus t, let's say, times this sinusoidal term, a times cos omega t plus b times sin omega t. And this, if we sketch, would look like this. So this is basically a decaying exponential, and we can see that in the end, the system, the impulse response of the system will go to 0. So we conclude that this system is bipolar stable. But if we have poles on the imaginary axis S equals j omega, so the impulse response of this would be ht is a times cos omega t plus b times sin omega t. So this would be 0, right? And we basically do not have this term anymore. And we now have only the sinusoidal signal, and the response is oscillating. And it is called marginally stable. So if we have bounded input, it will result in bounded output as long as the input is not a sinusoidal signal with the same frequency. So this is what we call marginally stable. So it's not going to 0, but it's also not going to diverge. So it's just a perfect sinusoidal signal without any decay or any growth. So the next phenomenon here is the simple poles in the right half plane of S domain. So in this case, we have this being positive, so the entire power here would be also positive. And in that case, we can see that um, given that the given the bounded input, here the response will be unbounded. So this is a growing sinusoidal, and this is what we call the bibo unstable. So the okay, sorry. So the impulse response here would be something that goes to infinity or minus infinity. So this would look like this. And the given bounded input here, the response of the system becomes bounded, or in other words, the system here is viable, unstable. So again, it depends on the location of the poles in the relation with the imaginary axis. So if the poles are on the left of the axis, we can um, conclude that the system is stable, bistable. But if the poles are on the right of the axis, so note that what if we have, okay, so what if we have two poles? Say one of those is here, the other is here. Well, the system is still unstable. So um, uh, for the system to be stable, all poles have to be on the left. If we have even one pole out of, let's say, many poles we have on the right of the imaginary axis, the system becomes viable, unstable. So those are the simple poles, or if we have the poles that are not repeating. Then, if we have the poles that are repeating, so we call this a multiple order poles. And here, the multiple order poles in the left half plane would be minus sigma plus j omega to the power of m. So we have many or several poles here in the same value. And here the impulse response would be t to the power of m times e to the power of minus sigma t times a cos omega t plus b sin omega t. So we have actually two terms here instead of one outside of the bracket, outside of the sinusoidal. The first one is the um, exponent t to the m. So if m here is, let's say, 2, if we have two poles in the same place, we will have this. But also we have e to the minus sigma t, which is pushing this to 0. So we have this e to the minus sigma t will be like this. And in the end, everything that we have here in t to the power of m will be multiplied by something that's very small, since t here is, of course, advancing. And then we will have this term here will be going to 0. So this t to the m is not as dominant as e to the minus sigma t. So the exponential term here would be more dominant rather than the term t to the power of m. So yeah, the decay of the exponential component therefore is faster than the increase of t in polynomial terms. So therefore, we can conclude that the system is also stable. So that's for the uh, multiple order poles in the left half plane. But for the multiple order poles on the imaginary axis, we now have S is J times omega to the power of M. And here the impulse response is ht, which is t to the m. Again, similar to the previous case, so this one would be set to 0. So this would be a cos omega t plus b sin omega t. And then we can see here that the polynomial term does not have anything that will, let's say, cancel this to zero. So we will have the growing exponential, growing sinusoidal signal. I mean, so since this is going to infinity, so A cos omega t plus B sin omega t would be multiplied by something that gets larger and larger over time. And we can see that this system is viable unstable. And then we have the next case with multiple order poles in the right half plane. So here we have positive sigma, so negative. And the impulse response would be ht equals, yeah, of course, we just replace minus sigma here to sigma. So t to the m times e to the sigma t times a cos omega t plus b sin omega t. And it's clear that both of these two terms are going to infinity um, by the with the increase of time. So this system with such impulse response is unstable since the response increases for increasing time t. Okay, so we have some examples here. So, for example, we have this. Um, okay, so yeah, I forgot to say that we have poles and we have zero, but for now, let's focus on the pole because it's more important for the stability of the system. Later, we could utilize the zero by let's say, in order to improve the stability of the system, but we are not going to go into that in this course. So the system stability here of this differential equation of y double dot plus 5y dot plus 4y is minus 2x plus x dot. So the transfer function here would be, oh, sorry, I think I made a typo. Let me fix this quickly. So this should be s to the power of 2 and this should be just 5s. Okay, sorry about that. So we can factorize or decompose this into s plus 1 and s plus 4. And here the poles are located. So there are two poles here. One of them is in minus 1. The other is in minus 4. So yeah, since both poles are located on the left of the to the left of the imaginary axis, we conclude that the system here is viable, stable. And then the next example here, we have the stability of this system represented by this transfer function. So Hs is s plus 2 over s squared plus 2s plus 1. So the transfer function here, we then factorize this into like s plus 1 square. So we have s plus 2 divided by s plus 1 square. So we have repeated poles or multiple poles at s minus 1. So s is, of course, minus 1 in order to make the system here having zero denominator. So here the system is viable, stable, since, of course, the poles are both to the left of the imaginary axis. And this would be the impulse response if we perform the Laplace transform, inverse Laplace transform here, and then we get this explanation where the exponential component here is more dominant than the linear one with t. So if we have e to the minus t, of course, it's going to 0. If we have t times e to the minus t, it's also going to 0, but it would be a little bit slower because we have time t also. Okay. Yeah, so the next example here, we have the transfer function hs is s squared plus 6s plus 5. And the denominator is s times s square minus 4s plus 5. So here we have two poles, sorry, three. um, One is at 0. The other two are a complex pole. So the poles are 2 plus minus j. So we have like this complex conjugate form because we want to have in the end we will always have non-complex multiplication, right? So if we have complex conjugate, we multiply those complex conjugates, we will end up removing the imaginary part. So anyway, so the roots here or the poles are 0 from this, and 2 plus minus j. So 2 plus minus j would be a positive, would be, having a positive real um, value of the poles. So here the system is unstable or not stable since the complex pole has positive real parts. So yeah, that's how we determine stability by looking at the transfer function of the system. All right, so transfer function itself is, well, the one that we have seen already. So convolution of the, okay, sorry, convolution of Laplace transform here. This enables us to update the system's response easier, where we could derive the transfer function, and this transfer function, well, they could be obtained from impulse response, differential equation, and the equations in S domain. So the output of the system with impulse response ht and the input xt is yt is the integral convolution here of x tau and h v minus tau. And if we perform the Laplace transform of both sides here, so we will have like ys is hs times xs. So we have this simple um, say diagram, showing that, okay, this is where we have the transfer function. So 0 here is the root of the numerator h, and pole is the root of the denominator of h. So for example, if we have this ht is 5e to the minus 2t plus 2e to the minus 10t ut, the transfer function here is, well, hs is the Laplace transform of ht plus transform of 5 times e to the minus 2t plus 2e to the minus 10t. So we can just get like 5 per s plus 2, right? Because this term will result in s plus 2, and this would be 2 per s plus 10. Because this term will result in s plus 10, e to the minus 10t, and we have two poles here, minus 2 and minus 10, and to get like the 0 here, we need to add this these two fractions together, um, and we uh, have like a 7s plus 54. So for example, this would be 5 s plus 10, and this would be 2 s plus 2. So 5s, right, plus 50 plus 2s plus 4. So this would be 7s plus 54, and we get the poles being minus 2 and minus 10, and the 0 being minus 54 per 7. So based on that, we can actually see the um, system properties, also the region of convergence, and the stability of the system. So for a causal LTI system with HT is 0 for negative time. And here we have the right-sided signals, and the ROC, or the region of convergence, here is the right of the rightmost pole. And for the left-sided signal, or also the anti-causal LPI system, so HT is 0 for positive t, we have the left sided signals, and the region of convergence is to the left of the leftmost pole. And for the stable LTI systems, the region of convergence HS has to include J W axis, where the real value of S here will be 0 in this axis. And for a causal and stable LTI system, so causal here, this one, and this is the right-sided signals, right? So the region of convergence need to be um, also including the j omega axis, and in other words, the transfer function here, they have to contain the poles that are located in the left half plane of S domain. So that's the relation between the system properties, the region of convergence, and the stability. So an example here is if we have a system with a transfer function Hs is s minus 2 per s plus 2 times s minus 4, we could have several conditions, whether or not the system is stable, depends on the causality, and of course the region of convergence also be different. So this, for example, we have the poles minus 2 and the poles 4, right? So for the poles minus 2 and the poles 4, so for this case we could have the system being causal. So both of these signals are uh, right-sided. So we have the region of convergence here to the right of the rightmost pole, which is 4. And since the region here does not include the axis, the system is not stable. And then if both signals are left-sided or anti-causal, we could have the ROC here being to the left of -2. So this would be the case of both signals being left-sided, and the same as the previous case, here we see that the system is not stable because the region of convergence does not include the imaginary axis. Then for the third case, now we have this signal being right-sided or causal, and the signal here being anti-causal. So in this case, we have the ROC here to the right of -2, but to the left of 4. So because of that, we could have the uh, a stable system because the ROC here touch or include the imaginary axis. So from this example, we can see that the region of convergence depends on whether or not the system is causal, and also it will affect the stability of the system. All right, so the next aspect of this is the transfer function and Laplace of the differential equation. So this one shows, so this explanation shows that the transfer function here, they are obtained from the differential equation. So if we have this constant coefficient differential equation, we could perform a Laplace transform in both sides, so the output side, also the input side, and we by linearity properties we can perform the Laplace transform of each terms, and then we have the bunch of summation of s to the power of k here, and the ratio hs is ys over xs, is basically the polynomial of bk times s to the k and ak times s to the k, with the impulse response ht being the inverse Laplace of hs. So this one is how we obtain the transfer function. And we could also obtain the transfer function here by looking at the system in a more direct manner. So here we could perform the Laplace transform, and we could perform the elimination in S domain. So for example, we have Hs and Ht. Sorry, this should be N. Okay, so this should be and HS and HT for the system with EI as the input, the output is V RC, and the initial condition here is 0. So we have R equals 1, L equals 1, and C also equals 1. And here, by Kirchhoff law, or by even like the um, voltage divider, we get these equations. Uh, so EI is L times di dt plus IT times R plus 1 per C integral IT dt, and VRC, or the output here, is IT R plus 1 per C integral IT dt. So that would be the equations, and if we perform Laplace transform in each of these equations, so we will have L times S times I plus I times R plus I over or divided by S C, because this is integral, so we have 1 per s. And the second equation here is VRC is I times R plus I per CS. So this would be R plus 1 per CS. And the current here is IS equals to SC plus or per RCS plus 1 times VRC. So by um, eliminating or by rearranging rather, so we have the I is VRC divided by this, and I here is SC per RCS plus 1 times VRC, and then by substituting this I to the first equation of EI, we get the LS times I plus I times R plus I per SC. So here we have EI by substituting again I S square LC plus SRC plus 1 divided by RCS plus 1. So H, which is the transfer function, here is the output divided by the input. It's P RC, so it should be like this. Okay, sorry. Okay, is RCS plus 1 divided by S square LC plus S RC plus 1. And since every component has the value of 1, this would be S plus 1 per S square plus S plus 1. And HS here is S plus 0.5 per S plus 0.5 square plus 0.5 square root of 3 square. So yeah, this one is rather maybe um, complicated, but I think yeah, we have already the value of the transfer function. So this is just some factorization, which yeah is indeed like not very methodical. So you have to try and guess what kind of um, factorization that we can get from this. So here HT is the inverse Laplace of HS. So this would be this part here. By looking at the table, we get like a e to the minus 0.5 times cos this 0.5 square root of 3, and this would be 1 per square root of 3 times e to the minus 0.5t times the sine of 0.5 square root of 3 t ut. So yeah, yeah, again we have to look at the table, so to see, for example, what kind of um, pairs that we could obtain by looking at um, this transformation, Laplace transform here. So yeah, that's the terms that we are looking at. Uh, okay, so where are we? Okay, so here, so the impulse response will be like this. So yeah, that's how we use the Laplace transform and the transfer function. Similar, very similar to the Fourier transform. And here we have to, yeah, we have to perhaps do some practice to be more familiar with the, yeah, Laplace transform pairs, or the yeah, corresponding Laplace transform of the some familiar functions. All right. So that's for the transfer function. So the last topic here is the block diagram. So block diagram of the continuous time system. So the block diagrams here, they are used to describe the functional relation between components, and to simplify the interconnections of the system. So, for example, here is the block diagram of the DC motor control, where we have the input, which goes to amplifier, and then the output is, yeah, sorry, this is in Indonesian, but this is the DC motor. We have the noise here, or the perturbation, and we have the load. The output here is the speed of the motor, which depends on the input, right? So there are some elements of this block diagram. For sure, we will have the block, as the name suggests, and this is in S domain. And then we have the summing points. So this one is the summing points, and we have the takeoff points. So this one. And then we have the line with arrow that determine the direction of the signal. So yeah, the signal here has a direction. So it's not like just just this like this um, bunch of line. So they need to have arrows. Okay, so they need to be like this. And yeah, I think those should be enough to um, illustrate or represent our system, what the input is, what the output is, and so on. All right, so some little procedures here to design a block diagram are some fundamental operations, operators, constant gain, K, and the integrator 1 per S. So the steps, as we have seen before, would be to obtain differential equation of the system. Then we obtain the Laplace transform of the differential equation, and then we design a block diagram from the obtained algebraic Laplace equation. And if you remember where we discussed the simulation diagram, this is very similar. Well, this is yeah, basically simulation diagram is like a more practical form of the block diagram. But nowadays they are very similar. We cannot even like differentiate those. So this is the example of the block diagram with summing point and the takeoff point. Here the summing point is, well, we sum this R and C times H, and the takeoff point here is yeah, the C here. So the C here not only becoming, let's say, the output, but they also become, or they are also fed to the HS, the block HS. So they are going to two different directions, to the right and going back here. So yeah, this is the summing point and the takeoff point, and this is the typical block diagram of a system, perhaps a more complicated one. And we, yeah, can look at the interaction between several elements of the system by looking at this block diagram. So here, next example is to show the block diagram of the RLC system, where we have zero initial condition. So yeah, very simple again, electrical circuit. Now the output is the capacitor, the voltage in the capacitor. So we get the differential equations from the Kirchhoff voltage law. So we have xt, the input is it equals to, or we can say like minus xt plus it times r plus L times derivative of it plus 1 per c integral of it equals to 0, and we can move minus xt to the other side of the equation. Then the second equation would be yt is 1 per c integral it dt. So this is standard for the capacitor again. And if we perform the Laplace transform in both of these, we have xs is r times I s plus ls times I s, because this is the derivative, plus I per SC, which is the output. So Y here is I plus, or I per SC. So yeah, when we um, divide everything here in the first equation by r, so this would be divided by r. We have like x minus, so this would be y, so this would be y, so x minus y, and then minus lsi per r, so this is I from this ri, and then we can get several blocks here. So the first, or maybe the easiest one, is this block from the output. So y here is I divided by sc, which is this. And okay, let me just erase. Then the yeah, so that's the second equation. Then the third one here would be represented by um, this figure. So we have y, we have x, we have lsi. So this would be minus y, would be minus lsi, and this would be x. Uh, and then this would be divided by r to get I. So this is, um, okay, sorry, 1 per r times I, right? Uh, and this is I, okay? So, sorry, I mean 1 per r times everything here will result in I. So from these two figures, we can merge and we can get this um, block diagram. So we have X, Y, and we have 1 per R, we have SL, we have 1 per SC here. So we just joined this together. So this will go into this, and this will go into this, right? So that's how we get the block diagram of the system. Yeah, sorry. So then the next example here is the configuration of a diagram. And we are given this differential equation, and we um, need to draw the block diagram for this LTE system represented by this equation. Well, similar to the simulation diagram in the earlier parts of the course, here we have the um, two types of solution. So the first one is this form. So we can get like the s square y. So of course we first use the Laplace transform to get this um, solution. So to get this frequency domain equation, so s square times y, then we group this together, s square times 2x plus s times minus 3x minus 3y. Then this would be added by x minus 10y here. And then we divide everything by the highest degree polynomial, which is s squared. So y here is 2x plus s to the minus 1 times minus 3x minus 3y and plus um, s to the minus 2 times x minus 10 y. So the um, block diagram would look like this. So that would be the first type solution. And yeah, the type 2 solution here, we use other variable phi. So phi double dot plus 3 phi dot plus 10 phi is x. And also we have the second equation here. So the second equation here would be using phi to get y. So y is 2 phi double dot yeah minus 3 phi dot plus phi. So this is the block diagram of the type 2 solution, and we perform the Laplace transform of both equations here, and we get s square times phi, which is minus 3s phi minus 10 phi plus xs, and ys is 2s square phi minus 3s phi, because this is phi dot plus phi s, which is the Laplace transform of phi t. So yeah, that would be the configuration of block diagrams. We can do the opposite by looking at this block diagram. We can get the equation. So the yeah, this figure we can see like, okay, this is y is say x times 2 plus, let's say, x, right, minus 10y, right, x minus 10y, and that would be multiplied by 1 per s, so s to the minus 1, and this further be added by minus 3 times x, and also with minus 3 times y, which will then be multiplied by 1s. And this will be added with 2x. So similar to this, we have phi here. So this would be phi dot or s phi. This would be phi double dot or s square phi. So s square phi would be minus 3s. So s square phi is this, right? So it's like x. So this is x. So this would be minus 3 s. So minus 3 this s phi or phi dot. Also minus 10 phi. And y is actually 2s square minus 3s plus phi. So that would be the block diagrams of these two examples. Oops, sorry. So one more slide, or two more slides rather. So we can also perform algebraic operation, the block diagrams. Here we see that a system, they consist of several blocks or subsystems that are related in series, parallel, or feedback. And in as a domain, the transfer function that describes the subsystems relations could be determined using algebraic equation. So the example here for series, we have H1 and H2, and then we multiply this to be H1 times H2. This is the series relationship. And then for parallel, we have H1 plus H2, which will result in, okay, so this is being H1 from the first system and H2 from the second system. And the third one is the feedback relationship, where we have the first transfer function H1, the second transfer function H2, and we get that this could be simplified with H1 per 1 plus H1 times H2. So yeah, those are the um, like the basic relationships of the functions related by block diagram. Okay, so here one last example is that we obtain the transfer function of the system. We are asked to obtain the transfer function of the system and the step response of the system. So we have the input XS, and we have the this part is the one with feedback. So this is the one with feedback. We have 1 per S plus 2 and 1 per plus S per S plus 2. So if we think of this as H1, uh, so we think of this, where is this, sorry. Uh, okay, okay, so this is H1. Let's say that this is H1 and this is H2. We can get the relationship of that. So the relationship of this is H1 per H1 H2 plus 1. This is H1. So 1 per S plus 2 per 1 per S plus 2, right, times S. So S per S plus 2 plus 1. And this would be the same as this. So this would be, yeah, 1 per S plus 2, and this would be 1 plus S per S plus 2, right? And this is the feedback part. We still have the series part, which is simple. We just multiply this with the transfer function here, which is 1 per S. So this is X and this is Y. And if we multiply this, we end up actually having half per S times S plus 1. So if we multiply this, sorry, I will try to do it here. So this would be like a 1 per S plus 2 per, so this would be S, right, plus S or plus 1, right, per S plus 2, because this is multiplied by S. Sorry, so this should be S square, right? So if we then get like a 1 per S plus 2, we multiply this with S plus 2, so we will get S plus 2. So this would be plus S square per S plus 2, right? So this would be 1 per S plus 2 plus S square. Okay, so it seems that I made some mistake. Let me check. Okay, so actually I'm correct. So this would be 1 per S square plus 2S plus S square would be like 1 per 2S square plus 2S, right? So this would be S times S plus 1 times half, right? 1 per 2S square plus S. So this is a half, and this is S times S plus 1. So if yeah, xt is ut, then we get the input xs being 1 per s with the response ys here is half divided by s times s plus 1 times 1 per s. So we multiply this again with 1 per s because xs is the input. um, so we multiply this with the input here, which is 1 per s. So that would be half times s squared times s plus 1. And if we perform the partial fraction decomposition, so we get this minus half per s plus half per s squared plus half per s plus 1. So that would be the output, and then to get the output in time domain, so the inverse Laplace transform of this would be minus half, right? Because this is unit step, this would be half per s square is half times t times ut plus half times s plus 1, which is half, half divided by s plus 1, which is half times e to the minus t ut, because this is half, so this would be like a half times 1 per s plus 1. So this one has this corresponding pair. All right, so that's about the Laplace transform. We obviously have studied a lot, beginning from the definition of Laplace transform, also the region of convergence, how we can have more than one Laplace transform, like a frequency domain function for the different time domain function, and also we look into the characteristics, also like the inverse of the Laplace, inverse of Laplace transform. Also, we could look into the first step, I think, to study system, important step, which is to determine the system stability, to look at the poles, and also we can, or we did the analysis of the transfer function by looking at the poles, looking at the ROC, to see how the system's stability is. So then we have the elimination of in S domain. So to analyze the system, we may need to perform eliminations in the context of differential equation, and this S domain would be a good alternative to obtain the transfer function and the inverse, or the impulse response. And then we also studied the block diagram of the continuous time systems, and also we look into some configurations, also some algebraic operations. And yeah, the reference, of course, you can get this from the textbook. Also, there is like one nice video about the Laplace transform, which you can take a look into, and many others. All right, so then I will just touch into this shortly. So after studying the continuous time system, then we look into the discrete LTI system. So the okay, let me just stop share and share the correct one. Okay, so I think it's this one. We will, yeah, discuss about this next week, or yeah, by the time you watch this, is probably yeah, in basically in the class number 11. So the discrete LTI system here, in some sense, they are very similar to the continuous LTI system. And we have, for example, the signal representation in impulse form, which is a very important tool for the signal analysis and LTI systems. So, of course, in discrete time systems, we do not have the value for the entire time. Instead, we have the values only for um, some specified time, often like integer, or the times defined by the sampling process. So this we will continue in the next class. I think now it's better to focus on the exam, which will be done, which will be held on Monday. So the material here is until the Laplace transform, and you have the chance to make like a cheat sheet, which you can use later in the exam. So the details I will post in my ITS classroom or in WhatsApp. And to get your attendance, make sure that you work um, on the short exercise, which also you can find in my ITS classroom. So yeah, thank you, and I will see you next time. Uh, Bye.